Good morning. Okay. This session I will explain about the OPM applications in chapter 11 of this book. Okay. So after we learn about the basic OPM and we know the some parameter in operation amplifier is like gain and then a bandwidth and then a common mode rejection ratio and also input and output offset, then we have to know about the what is the op-amp applications, because the operation amplifier is very useful circuit or devices that we can it's like we can use the op-amp for many applications, not only in the electronics, basic electronics. We can also use in power application and also instrumentation engineering. And so this is some example of the op-amp application in the circuit. We have a constant gain multiplier, voltage summing, voltage buffer, control source, instrumentation circuit, and active filter. Okay, we start with the constant gain amplifier, and in constant gain amplifier we have a kind of the circuit. The first one is inverting versions, like we already discussed in the basic op-amp, and the output of the inverting inversion is AV is equal to minus RF per R1. So the output of the circuit of TO will have the different phases of 180 degrees. So the phase difference between the output and the input is 180 degree, and the gain is depends on what is the RF parameters, as also what is the R1 parameter. And we have another topology or another circuits for the amplifier, that is a non-inverting variations. And in non-inverting in what is the differences between the inverting version and non-inverting version? In a non-inverting version, the input is connected to the V1, okay, and connected to the negative terminal of the op-amp. But for non-inverting amplifier, the input is connected to the ground, and the input, eh, not the input, the R1 is connected to the ground, and the input is connected to the positive terminal of the amplifier. So the total gain of this non-inverting version is AV is equal to 1 plus RF plus R1. So we have to decide what is the value of the RF and R1, and then we can get the gain of the amplifier. And if we want to construct or design the multiple stage gain, we can connect op-amp. It's like a series op-amp. For example, if we put a series op-amp for the 3 stage, so we can multiply all the amplification of each configuration. So the total gain, or A, is equal to A1 plus A2, A1 multiply to A2 multiply to A3. And you can see here for the A1 is non-inverting version, R2 is inverting version, and then the last stage also inverting version. So this is a three serial op-amp configuration, and we can calculate total amplification of this op-amp. And then another application is voltage summing. Uh, this is the if we want to make a summation of the input. For example, we have a 3 input here, V1, V2, and V3, and we want to make a summation of V1, V2, and V3. We can use this op-amp. So V0, VO, I mean that the output value of this circuit is equal to minus RF plus R1 V1 plus RF per R2 V2 plus RF per R3 V3. because this is inverting op-amp, so it will be negative. The phase difference between the output and input is 180 degree. So this is the for the if we want to sum the input voltage of the op-amp. And then another application is voltage buffer. This amplifier is no gain or loss, so we didn't put any gain in this circuits, or we call it unity gain amplifier. And the advantage of this using unity gain amplifier is we have the very high input impedance like op-amp characteristic, and then we have the very low output impedance. So if we realize this very high input impedance and very low output impedance, we can realize using this topology, or we can design with using the similar R1 and RF using the non-inverting version or inverting version to avoid the offset problem. So this is a voltage buffer, and then the voltage buffer we put or we use the voltage buffer sometime as the output impedance. So after we construct or we design the amplifier, and we want to connect this amplifier to another devices, so we have to lowering, or we have to reduce the impedance, so we can use the voltage buffer, because the voltage buffer has a very low output impedance. And then we have another circuit like a control source. We have four kind of the control source. The first one is voltage control voltage source, and then voltage control current source, current control voltage source, and then the current control current source. For the voltage control voltage source like this one, yeah, basically this is like non-inverting inversion amplifier version, like I explained before, and then the output is depends on the RF and also R1 multiplied to the V1, and then this and also we can use the inverting amplifier version and also non-inverting amplifier version like the picture before. And this is the another topology is voltage control current source. In the output, we didn't look at the what is the output voltage, but we look at the what is the output currents. So we're using the inverting topology like this one, so we can calculate what is the I/O, the output current, by using VI per R1, because of the current flow here, E1 for example, is similar to the I0. So we can get the output current is I/O is during V1 per R1. Or we can simplify by using the K dot V1, and then K is the 1 per R1. And then another version is current control voltage source. So the output is, we look at the what is the output voltage is equal to minus I1 RL, and then we can determine what is the V out by using this equation, because of this is the inverting version, and then because of the V in per R1, this one, this mathematic is I1, so we can make a simplification that the mathematical of this circuit become the V out is equal to minus I1 RL. And then the last one is current control current source. In current control current source, so we look at the what is the uh, relation between the output and the input, and we know that this is the inverting version, so V out is minus RF per R1, and then RF per R in dot V in, and then R in is this one, R1 is parallel to R2, so we can use that V out per RF is equal to minus V in per R in, and then because of V out per RF, this one, is the I/O, so we can change that V out per RF is I/O. I/O is V in minus V in per R1 parallel to R2, and then R1 parallel to R2 is this equation, so we can replace it, and then I/O become minus V in per R1 dot R1 plus R2 plus R2. So we can get that V in per R1 is the I in, so I/O is equal to minus E multiplied to 1 plus R1 plus R2. So this is like a constant, 1 plus R1 plus R2. So we can get that I0 is equal to KE, where the K is this one, R1 1 plus R1 plus R2. So this is the current control current source. And then this is the example for instrumentation circuit like display driver and also an instrumentation amplifier. And this is the topology of the display driver. So please look at the reference. What is the working principle of display driver, and also the instrumentation amplifier. Okay. Okay. Then we have another circuit using the op-amp is the active filter. The active filter, we have to add the capacitor, and then this capacitor can control the cutoff frequency. So the op-amp filter can provide a controllable cutoff frequency and also controllable gain. We have some circuit topology of the active filter. The first one is low pass filter, and then the high pass filter, and then the band pass filter. For the low pass filter, we have a two order. The first one is first order, and you can see here this is the this is the non-inverting amplifier. This one is non-inverting amplifier, and then we connect the input voltage using the RC filter here. So this is the input voltage connected to RC filter, and then using this configuration we can calculate the cutoff frequency, or FOH is 1 per to VR1C1, and also the AV again is 1 plus RF plus R1. The RF is this one, the R1 is this one. So if like in the class assignment that you have to design the low pass filter for the specific frequency, so you can using these equations. And also for the gain, we can put a more gain in this active filter. But if you have to design the pure filter, I mean that the AV is equal to 1. So we have to neglect the value of this one, the second parameter must be equal to or equal to 0. So it means that you have to choose that the RF is much more smaller than the R1. So the FV is equal to or equal to 1. So you can use the many option. I mean that you can choose a many option of the circuit using this configuration. And then also for the second order filter, what differences it is we put another RC filter before and after the input voltage here. So we can make under roll off of the filter can be made a stepper by adding the Morse RC network. And for the high pass filter, this one, so the we put the R1 and C1 is like this one. So the C1 is connected to the input voltage, and the R1 is connected to the ground, and we can calculate the cutoff frequency of the high pass filter using this equation. KOL is equal to 1 per 2 VR1C1. And also you can use the second order by add more the RC filter after the input voltage. And then if we combine two configuration, high pass filter and low pass filter in this section, we can design the band pass filter. This one is the high pass filter, and then this one is low pass filter. So we can get the configuration of the frequency like this one. We can define what is the VOL or the low pass frequency and what is the high pass frequency. So I think this is the all of my presentation for the open application. Thank you for your attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.